So this is page 114. The electrolytic cell is non-spontaneous, and so is thermodynamically unfavorable. Oops, ran out of room. And you can see that the actual half reactions, the oxidation and the reduction, are switched. Okay? Because if one of them is spontaneous, the other one is going to be non-spontaneous. And if it is spontaneous, what can you say about delta G? Delta G is negative, so delta G is less than 0. And for an electrolytic cell, it is greater than 0. So that's the overall summary between the two of those. Here's another little comparison chart. A voltaic cell has to be separated into two half cells. Why is that? We can do an electrolytic cell in one container, but we have to do a voltaic cell where we separate the two half cells. Chat with your partner about that. See if you can come up with a reasonable explanation. What if we put our copper 2+ right in the same container with our zinc? They just do their thing. We get Cu. This comes off as Zn2+. The electrons just do the transfer right at the surface. And are they going through a wire? No. And the whole point of having a voltaic cell is we would like to force those electrons through a wire in order to get some useful work out of them. So if you have everything all in one beaker, the electrons won't have to go through a wire, which is why instead of having the copper ions right here, we would instead put the copper ions that want to take the electrons over here. So then for the electrons to leave the zinc, they actually have to go all the way through the wire over to the other one. Is good? Okay. So a voltaic cell is a battery. An electrolytic cell needs a battery. I'm also going to put or a DC power source. Now, do you guys know what a power source is? It's a source of power, yes. Literally, it's kind of like a box that you plug into your outlet. Now, do you guys know what kind of current we get through our outlets? Alternating current. Now, your physics teacher would tell me that I'm wrong. This is not what alternating current means, but I always imagine in alternating current that the electrons are doing this. Yes? They're going back and forth. They're alternating. Yes? Is that going to provide a push in one direction for the electrons to flow? No, because they're like going back and forth. So what a power source does, a DC power source, it takes the alternate current, and through the magic of electronics, it transforms it into direct current so that it's pushing electrons one direction. So sometimes, because we need to provide a different amount of power to get the electrolytic cell to go, you might not have a battery that suits that purpose. Yes? So if you need to provide, 4.07 volts, it's nice to just be able to take the knob on your little DC power source and turn it up until it hits 4.07 volts, rather than trying to assemble the right number of batteries in series to make that happen. Yes?
So we need to plug them into a wall to make the wall work. Why even have alternating current?
Oh, because the alternating current works fine for most things, but it doesn't work for driving batteries backwards.
How does it work?
I do not know. That is a physics question for your physics teacher. Yes? Yes.
I just heard the electrolytic cell. What do we use it?
What do we use electrolytic cells for? So we use them for purifying ores. So like you will be separating out, say, iron from iron ore. Copper comes like mixed in with all kinds of other metals, and so you can purify the copper. We'll be going into details of that a little later. If you want to get say, hydrogen gas and oxygen gas, you can split water into hydrogen gas and oxygen gas. So it's good for splitting. It's good for getting pure elements that don't necessarily come in pure elemental form. It's hard to get pure sodium because sodium just wants to give away its electron, right? So one of the ways you can get it is by taking molten sodium chloride and splitting it into Na0 and Cl chlorine gas 0. So getting elements on their own, purifying ores, and we also use it for electroplating. So if you want a thin layer of one metal on top of another metal, it does that as well. And we'll be looking at that in more detail in just a bit. Okay? Yes.
So what makes the power source have, what makes the electron in it just like that?
In the power source, like literally you're using the alternating current, you're using the energy from the alternating current, and through the magic of electronics, it turns it into a pushing force one direction rather than the energy doing what it does. Yes. Yes, batteries are always spontaneous. In fact, you could build a system where you have literally one of these attached to one of these, and you can have the galvanic cell powering your electrolytic cell. Okay, you just have to make sure that the galvanic cell provides enough voltage to make the electrolytic cell run. Okay? Keep the questions coming because I know this stuff is a little bit like when you first start. Yes? You need as much voltage. You need to overcome the negative potential. Okay, so you remember last day we found E0 cell for the electrolytic cell and it was like negative 4.07 or something. So you need to make the voltage positive, even just like the tiniest, itsy bitsiest bit positive. So you would provide 4.07 positive volts plus a tiny bit to make it go. Okay? So basically, if you've got a ball and it's about to roll down the hill and you just hold it, the forces are equal, yes? But you need to push it just a little bit more to get it to go up the hill. It's the same sort of principle. So power source or your battery needs to push uphill with just a little bit more energy, then this thing is negative. Yes? Okay. The voltaic cell produces electricity, powers other devices. The electrolytic cell is forced to occur by the battery or DC power source. The E naught of the cell is positive. The delta G is negative for a spontaneous cell. Okay, so this is for your galvanic cell. All of these on this side are galvanic, but I've run off the top, so I just want to remind us these are all galvanic. And these two over here, we have a negative cell voltage. That is electrolytic. And if delta G is positive, we have an electrolytic cell. I don't think you're going to have to label your cathode and anode as positive and negative. I don't think. I'm not 100% sure. I haven't seen it in recent years, so I think we're making a pretty good bet that we don't have to, okay? But it confuses me, right? Because in an electrochemical cell, we label the cathode as positive, but the cations migrate towards the cathode. So like in my brain, that just doesn't compute very well. Yes? So I'm going to kind of put this in brackets. And I feel like if you're really, really concerned about it, I'll go find a video from one of the British instructors because they do a really good job of explaining things like this. Or if you're happy just saying, I don't need to worry about it, then you can just say, I'm not going to worry about it. So you make your choice. I'll decide, let me know. I will find you a video and we'll go through it next week if we want to. Sound good? I don't think you need to know it. Probably don't need to know. You definitely do not need to know it for regular chem exam. Yeah? Definitely not for regular. So those are all the things that are different. All the things that are the same. Oxidation occurs at the anode. Reduction occurs at the cathode. Where do electrons flow? From anode to cathode, and cations always move towards the cathode, and anions always move towards the anode. And if you know any one of those three things, you can figure out all the rest. Yes? All right, so predicting the products of electrolysis. If there is no water present, your life is good and easy, okay? If there is no water present, that means you have a molten ionic compound. It's going to be pure, so it's not mixed with anything. What does molten mean? Means it is a liquid. It has been liquefied, which we call melting. It has been melted. Now, if you've got an ionic compound, there's not much choice as to what can happen. If you have Na, which is positive, can Na be oxidized? What would it become if Na were oxidized? Na plus goes to Na 2 plus 2 electron, or plus an electron. Are we happy with that? That looks weird. Yes, it should look weird. It doesn't happen. Okay? Does not happen. No. Can Na plus get reduced? Yes, it can. Na plus an electron goes to Na. That looks good. That looks like a normal equation. We've produced something we've seen before, Na. Now, what if we had our chloride ion, Cl minus? Can chloride be oxidized? Yes, because if it was oxidized, we would get Cl minus. What would it become? Cl just normal. What is normal Cl? Cl2. And which means we would need to put a 2 in front of the Cl minus. And then we would have 2 electrons. And the answer is, can it be oxidized? And the answer is yes. This is a good reaction. Can Cl be reduced? Sorry. Can chloride be reduced? How are we feeling about Cl2 minus? Is that a thing? Nah. Okay, it's just not a thing. No. So when you have a molten salt, you've got a metal ion. The metal ion will get reduced. The non-metal ion will get oxidized. No choice. Very straightforward. Okay? So we would have, in this particular case, could you guys write the 2 half-cell reactions and then the overall reaction for this system here? So we're going to write the reduction, half reaction, the oxidation, half reaction, and the overall reaction. Why is it liquid? Because I mean, you could write it as NaCl liquid, but in NaCl liquid, I think personally that the ions are separate from one another. They are flowing around independently of one another. because that's the whole point of it being a liquid. Yes? Woo. Here goes chloride, here goes sodium. They're doing whatever they want to, yes? So that's why I would choose to write them separately. But you know, like it just depends what the question is asking. If it asks you for the ionic equation, then yes, write it as ions. If it just asks you write the equation, then it's your choice whether you put them together or leave them apart. Yes? Okay. Are we good? Cool. So that's really nice. Hope to heck that they give you a molten salt because that makes your life just super straightforward.
That would be good.
Now we get into the tricky stuff here. If water is present, in other words, if you have an aqueous solution of the ionic compound, the problem is that the ions can react and water can react. Water is on your reduction potential chart. Water can get oxidized, water can get reduced. And so we basically need to look at the reduction potential table to figure out which one is the preferred reaction. Okay? Basically, the overall statement is the higher the E naught, the more thermodynamically favored the half reaction. So if we are looking at the oxidation half reaction, we are looking for the most positive E naught ox. We're looking for the most positive oxidation potential. Now, does your table give you oxidation potentials? No, it gives you reduction potentials. So if you wanted to, you could also say it's the reaction with the lowest E naught red. Now, when we say most positive, what if we've got two negative values? Well, obviously, that's going to mean that you're going to go with the one which is less negative than the other because that's the same thing as more positive. Yes? I just put it there because, well, I need to use this for regular chemistry as well. And sometimes, you know, what's that? Yeah, higher would work. All right, next. So with our reduction potential, same thing, except for in this case, we are looking at the most positive reduction potential. In other words, the least negative if you're comparing negative values. So basically what you have to do, let's take a look at our example here. If you have a solution that contains lithium ions and nitrate ions, and we are using inert electrodes, what does that tell you about the electrodes? They're unreactive, so you don't actually have to worry about the electrodes reacting, okay? So you can just ignore the electrodes, which is kind of nice. There will be cases where you can't. So all you have to worry about is lithium, nitrate, and is there anything else in that beaker besides lithium and nitrate? There is water. How do you know there's water? because it says a solution. If you see the word solution, that means that water is present. So here's what you do. You simply list the species that are present. And you see, A, can they be reduced? Some of them can't be, right? Like Na plus. Oh no, Na plus can be reduced. Cl minus cannot be reduced, okay? Can it be reduced? And if they can be reduced, which has the highest reduction potential? Because whichever one has the highest reduction potential is the most thermodynamically favored, okay? So let's list our species. Li. We go and we look that one up on our table. It's pretty easy to look up. It has a reduction potential of negative 3.04 volts. Actually, take a look on your table for lithium. Where is it? Whoa! So do you think that lithium is going to be our favored reduction?
No.
Not unless there is nothing else present, okay? Because it's the lowest possible reduction potential on our chart. And I think it's the lowest altogether. Okay. So it's probably not going to be lithium. Let's take a look at nitrate and see what happens on the chart. We do have two nitrates on the chart, one at 0.96 volts and one at 0.80 volts. Yes, so there's a nitrate here and a nitrate here. However, what else do you see in that reaction with the nitrate? H plus. That means this reaction needs what? Yes, it needs acid to occur. If you're not providing an outside source or an inside source, like say it was HNO3, if you're not providing H plus, then this reaction can not occur, okay? So we can say, okay, that means that nitrate cannot be reduced. Neutral nitrate cannot be reduced. And that means we need to look at water. I've written down here, don't forget, if it says solution, you have water. If it gives X molarity, okay, you know, if it gives 0.1 molar, that means it's a solution. So those mean that water is present. So now water, the most used reduction of water is highlighted in gray on your table. I would like you to go and find the reduction of water on your table, please. Okay, do you guys see it? Yes? All right. So it has a reduction potential of negative 0.41 volts. Okay, so we are now going to compare negative 0.41 volts with lithium, negative 3.04 volts, and guess which one is better? Lithium. So lithium, or no, what? Don't mess with me. Water is better. Water is better, okay? Because negative 0.41 is higher than Li plus's negative 3 point, what was it, 04? 3.04. So we can say that water will be preferentially reduced. So when we're like, what's the reduction half reaction? It's that water half reaction. Is good? Questions? Yes. What is reducing H2O? Sorry? Yes, we're only doing the reduction half reaction. We're going to get to the oxidation one in just a second. Okay? Yeah, good question. So here's water. And one thing I'd like you to notice about the reduction of water, what is it producing? It produces H2, which is a gas. So if water is reduced, you will see bubbles. Yes? Now, what if you added some litmus paper near the cathode? What else does this reaction, this half reaction produce? OH minus. So if we were to put litmus near the cathode, what color would it turn? Blue, right? Because we've got that base there. Those are questions that can come up, okay? So this here, now, yes, they will migrate eventually, but it takes some time for things to actually do the migration. So the OH minus is originally going to be like building up around the cathode. And as time goes on, because this is happening at the cathode, whoops, reduction at the cathode. Yeah? Good question. All right, now we have another solution here. We have a solution containing Li plus and I minus ions, and they are undergoing electrolysis using inert electrodes. Which substance will be preferentially oxidized? This is a different situation now. So we have a solution. So you're going to list all the species present. Who are the species present? Species present, we have Li plus. What else? I minus. And H2O. So we're going to ask ourselves, can Li plus be oxidized? No. Right? It just doesn't make any sense. You cannot end up with Li2 plus. It does not exist. If we go look up I minus on our table, we get a value there, okay? Which direction would this reaction be taking place in, this half reaction? Forward or reverse for iodide? We are looking for the oxidation half reactions, yes? So in this case, this reaction with half reaction would be taking place which direction? Right to left. Okay, there is our oxidation. And if the number over here says plus 0.54, what is the potential of the oxidation? Negative 0.54. Okay, so we are looking at E naught ox of I minus is negative 0.54 volts. We also need water because it's a solution. Please go find water being oxidized on your table. We have to look for water on the right-hand side.
I appreciate there's like.
Oh.
Right? It's kind of nice, yeah.
Give me some money.
Okay, so we got water on the right-hand side over here. That means water can be oxidized. Again, it's highlighted in gray for you, so it makes it easier to find. AP will do no such thing, but it'll give you the potentials. Okay, it doesn't give you a chart, it just gives you whatever potentials you need in the context. Yes? And if it just says E naught and it doesn't on AP and it doesn't give you a value, assume it's a reduction potential unless they've specifically written the reaction backwards. Yes? So here's water. And what are we producing? Actually, let's go back to the other page. What are we producing when water is oxidized? We're producing oxygen, which is a gas. So what would you see? You would see bubbles if water is the thing being oxidized.
So we're gonna get a question like, you see bubbles in this thing, what is being oxidized?
Possibly, you might look at it and you see a picture with some bubbles and you'd be like, but yeah, you could. You know, if your other thing that's being oxidized does not produce bubbles. Yeah. Also, what else are we producing? Hello.
No, I'm just gonna listen to this example.
Okay. You're liking that chair, are you? Okay. Okay. So H plus, what would we observe if we put litmus near, and this is oxidation, right? So it would be at the anode. So if we put litmus near the anode, and if water is oxidized, what would we see? And that again is if water is oxidized. Yes. That's okay.
Like the reduction of offering water, the reduction of water is not thermodynamically stable. Not
Yes.
How does the auto-ionization of water?
Auto-ionization of water is not related in the least to this, because if you look at the products here, so let's look at our products of the oxidation of water. We get H plus and O2 neutral. What does the auto-ionization of water give you? H3O plus OH minus. Is there any oxidation or reduction taking place in the auto-ionization of water? No. Okay, totally separate processes, totally different reactions. Yeah? Okay, so here we go. We have looked at this. We have found the oxidation potential of iodide. We have found the oxidation potential of water because, of course, we have to take, what do we do with the value on the table? We have to make it negative because we're looking at oxidation. We have reversed the half reaction, so we have to reverse the sign. So who is favored? Iodide. So the oxidation of I minus is the preferred reaction. Preferred half reaction. Is good? Okay, cool. You just visited?
No, I was waiting, it's very kind of compacted.
No, you can talk to me now. Here, look, they're writing stuff.
I'm looking for some of your students.
You're looking for some of my students.
I don't
Why
know.
don't you talk to them? I recorded this. They can always come back and see what it is.
Oh, that's good. I'm not.
Oh, who are you looking for? Oh, hang on. Okay, I have a class list.
I'm very good at my job, I swear.
I'm like, you're sitting here very patiently. I'm like, you cannot actually possibly be going for it.
No, but it's great to watch a master at work.
Okay. Anyone else in grade 11 here? Yeah, Alvin, Ruth, Janet. Anyone else in grade 11? Okay, that's it.
Okay, so wait, which one again?
Alvin.
I'm gonna teach anyway, so I'll see you tomorrow morning.
Okay. Ruth, Janet. Isabel's not here today.
Okay, thank you, that's all. Okay, that's all you. You're not in trouble. Why would anybody think you're in trouble?
Huge trouble. Mr. Liang, nothing but trouble. Okay. Now, this is only going to matter on the regular exam, okay? Regular exam, because AP is not going to give you this whole list. It will only give you the relevant equations, so the relevant half reactions. So you don't actually have to worry about this. You don't have to be picking things out of the list. But in the regular exam, we have to take care if we have an acidic or basic solution. Let's find out why. Ooh, I want you to look and see what we have here in the nice gray highlighted one. And down below it later on, what else do we have? Feel free to look that up on your chart. Oh, yes, we have two reductions of water. One of them is nicely highlighted for you, and the other is not. Now, basically what happens is that the potential for the reduction of water changes if we put it in basic solution, and that's because OH minus is part of the reduction half reaction. So you will be at non-standard conditions. Yes? Yes. Yes, there should be a gas there. I don't know why it's missing. It just is, yeah. Hydrogen is never anything but a gas in the real world, so yeah. Okay. So what we're going to do is we're going to assume that water has a reduction potential of negative 0.41 if we have a neutral or an acidic situation. It doesn't matter if it's more acidic, if it's smaller than 10 to the negative 7 molar, it's not going to make that much of a difference in the potential. Okay? But if we have a basic solution, so for example, let's say you had NaOH. Yes? You would need to use negative 0.83. And you can sort of think of it in the same way as we were thinking about non-standard conditions last day. Yes? If we increase the concentration, now remember, don't use Le Chatelier when explaining on the AP exam in the written response, but you can feel free to use it when you're just thinking about what's happening to the voltage. If you were to increase the concentration of OH, which way would that shift, in big quotes, shift the system? Left. So what would happen to the voltage? It would decrease, yes? Because it's not going forward as much. Forward is producing energy, backward is using up energy, yes? So it's going to be less, it's going to be more negative. And as you can see, it is indeed more negative. Than neutral water. It is not as favored. Why is it not as favored? Because there's already some hydroxide around. Yeah? You don't need to explain that. You just need to know if it's basic, use the one without the 10 to the negative 7 molar. Okay? No explanation needed. So, if it is neutral or acidic, use this one. If it is basic, oh, that wasn't a highlighter. Oh. 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 If it is basic, you're going to use that one. Yes? And that's all you really need to know about it. Okay. Oh no, why? Oh, I didn't split the pages properly. That makes me sad. I need to fix the pagination. Fix pagination. Yes. It means what goes on what page, right? I've broken this lovely little explanation across a page. Like this was supposed to go on the previous page and somehow I've gotten out of whatever. Now, guess what? The oxidation of water also has two different reactions depending on, and can you guess what it depends upon this time? Whether we are in, not basic this time, but acidic solution, because this one contains hydrogen ion. So if you're in acidic solution, you're going to use this potential. And if you're in a basic solution, you're going to use this potential. Is good? Okay. A couple rules of thumb. You don't need to know these. But if you find them helpful, you can use them. Group 1 and 2 metals, metal ions, cannot be reduced in aqueous solution. Why not? Well, look, here's our group 1 and 2 metals, and here's water. Who is always going to win the reduction battle? Water. So you can just be like, group 1 and 2 metals are never going to be reduced because they're all at the bottom of the chart. You can also just look that up though, so it's not something you actually need to memorize. Our other hint, polyatomic ions do not get oxidized in aqueous solution. Number one, what happens with most polyatomic ions? They're all on which side? They're all on the left-hand side. So mostly polyatomic ions will be reduced rather than oxidized. There is one that's over on the right-hand side, but where is it? Go look on your chart and find SO4 on the right-hand side. See my little blue highlighting up there? Where is SO4 being oxidized? Way up at the top. Does that mean it's good at getting oxidized or bad at getting oxidized? Bad at getting oxidized. So if we're comparing it with water, it definitely loses. Okay? Is good? Okay. Type 1, type 2, type 3 cells. Where we've already dealt with a type 1 cell. Type 1 cell is where your electrolyte is molten. If you get a type 1 cell, you're going to be a happy, happy camper because you don't have to worry about water. So molten, liquid, melted. Also, the electrodes are inert. Can you guys remember a material that we might make an inert electrode out of? We might make it out of platinum. Okay? But I'm going to tell you now that if we have a molten salt, platinum is not as good a choice as graphite. Why? Because platinum melts. It might melt at that higher temperature. So graphite is a good choice. Graphite will not melt because all the carbon atoms are held together by very, very strong covalent bonds. Okay? So you have just the ions. You have your carbon electrodes. Could you please label the positive and negative terminal on that battery? Which one is which? Big one is positive, little one is negative. So what I'm going to get you to do right now is I am going to get you to, on your diagram, label the positive and negative terminals of the battery, the direction of electron flow, the anode and the cathode, the direction of the ion flow. So you're going to take the K and the Br and show which direction they move, and you're going to label the material the electrodes are made of. Go. Oh, and when you're done that, you're going to calculate the cell potential. Yes, of course. Check your cell, see if it looks like mine, and see if you got the same potential for the cell. Yes? Excellent. I mean, quite frankly, if you've labeled I find the easiest way to do this is to label the positive and negative, and then I make my electrons go the direction they would go. They move away from negative, and they move towards positive, and then I go, oh, my electrons move from the anode to the cathode, and my cations then move towards the cathode, and my anions move towards the anode. Like I said, if you know one of those things, you know all of them, basically. Oh yeah, you can, if they just give you words, you can draw a diagram, absolutely. In fact, it's very helpful sometimes. Yeah? Yeah. No, picture would be fine. Yeah. So now, what is the minimum voltage required by the battery or the DC power supply to make this cell run? Yeah, greater than positive 4.02 volts. So 4.03 volts, positive 4.03 volts would be good. Technically, if you just go anything over that, it's going to go. Okay? Yes? If you put in 4.02, I think it'll just stay there. I don't know. I've never actually tried it. Now, can I just throw your homework up on Teams?
Yeah.
Yes, and then you don't have to sit here and wait for me to figure it out? Excellent. Good.
That calendar meeting, right away.